Okay, so let's see. Here we have, this is posted, our third lecture, periodic table. And, okay, so, I just thought it would be interesting, to look at a few of the elements and, you know, we can, and in fact, I'm going to give you some assignment to look up some something like what I'm presenting because I literally cannot present 90 elements and talk about them. But I think it's important to take a look and especially historically. So we look at how long have people been on Earth? Several million years, apparently. So the people that were on Earth, what humans are distinguished somewhat by tool making. Although now we understand that, you know, some animals are making tools too. So the line between human and animal gets a little blurred. But here we have humans fashioned wood, stone tools out of wood, stone, and bone. Those are the materials that they used for millions of years. But in the last few thousand years, the kinds of materials were expanded through discovery of elements. So here is an example of an element that was used. I just like the picture. I just looked up where can I find pictures of interesting uses of copper. Um, Here is a picture of a vat in the Forbidden City in China. Now, apparently, these were used as anti-fire uh, protection. These were every day. There were people assigned to fill these vats with water. In the case of fire, they would be able to deal with it. Um, and these are mostly copper. I think some of them are gold plated, but this is basically a big copper pot. Now, how do we get copper? So much copper is not available freely, typically, in the earth. So there is material. Uh, okay, here, um, let me see something. Okay, I'll get back to it. Basically, the copper was obtained by heating a copper ore. And I mentioned it's in the notes. An ore is when a metal is combining with oxygen. It's very common, or other similar element, non-metal. So we have copper oxide, we have iron oxide, and we have sulfides. And so these generally are what are called ore. So if you heat these ores in the presence of carbon compounds, you can get the pure metal. You have to heat them at very high temperatures. Okay, so here is a nice example of bronze. Now, bronze is a mixture of copper and tin. And tin, the symbol, every element has a symbol. Many elements, like copper, is similar. It's Cu, at least it starts with a C. But tin, the symbol is Sn, which was originally stannous. Uh, so the symbol doesn't match the word in modern periodic table. But when you mix the copper and tin elements together, you get a material that becomes much harder, and so it lasts much longer and much more sturdy. Here is the famous sculpture I guess, around Wall Street. The bull, the bull of Wall Street. It's bronze. Okay, here is iron, and um, iron that's left out unprotected for a long time. It forms reddish, brittle substance, iron oxide. So all kinds of bridges and construction that are using iron have to deal with rusting, the formation of iron oxide, which weakens the material. And there are ways to protect uh, material from rusting. All right. So all the metals rust. You could have copper pipes. They're going to form an oxide. It's going to be like greenish. If you look in your house, you could see some greenish film on the pipes. That's going to be copper oxide forming. If it forms too much, the pipes will leak. It's no longer has enough structural integrity. Okay. Here is a mineral substance known as pyrite. It's got a kind of goldish hue to it, so it has another common name as fool's gold. Now, this is how sulfur was found. You take this and heat it, you can evaporate the sulfur and collect the sulfur from heating this rock, pyrite. Okay, so um, you know, many of these elements some of them were known um, in more ancient times. Some were discovered more recently, um, like the metals. Now look how recently phosphorus was discovered. We saw this picture before. This is an alchemist, and basically Henning Brandt, here he is, he's heating up the substance urine, of course, and he's getting phosphorus released, and phosphorus can glow. So he thought it was something really remarkable. So he thought he had discovered some mystical element like quintessence because of this glowing phosphorus. But you see, 1669, thousands of years later than, for instance, copper was known. Okay. What else do we have? Okay. So we did discuss the chemical and physical properties of matter. So I'm not going to do that discussion right now, but we'll back up and then we'll see the other background we need to talk about the periodic table. The background we need is basically understanding a little bit about the atomic theory and how is that related to mass. I did go through this a little, but it's very important for understanding the development of the periodic table. Now this is dealing with chemical property. So essentially here's the statement. Knowing the relative masses, look at this. This should be masses, allowed chemists to develop a list of atomic weights and formulas. So remember, every time hydrogen reacted with oxygen, it took a certain number of, an oxygen occurs in 2 atoms, and hydrogen is called diatomic, and so does hydrogen. So to get this to work, you actually have to have two hydrogen molecules and one oxygen, and here's the formation of the two water molecules. So the fact is that if you look at the mass, the relative mass is the oxygen is 16 and the hydrogen's is 1. So in a water molecule, the ratio would be 8 mass units of high oxygen and 1 mass unit of hydrogen, or 16 to 2. And so by doing these kind of experiments and measuring how the masses combined, that's how they developed a system of masses for the elements, by saying how did the relative masses combine. Now the trick is they had to know the formula. If it was just one hydrogen for one oxygen, then you would get a different number. And that was actually controversial. Dalton actually thought the formula for water was OH, which would lead to the incorrect relative mass. But anyway, in any case, there were ways to figure out the correct formulas. And through that, an added property which somebody mentioned, which was atomic weight. And so the two things that are very important are, besides all the other physical properties that we listed, like density and boiling point, are the formula, which would be H2O, 2 hydrogens for every oxygen, and the relative mass. The oxygen has a relative mass of 16 compared to the hydrogen is 1, and so forth. Nitrogen would have 14. So we amass all this information for many elements, about 60 or 70. It was available around 1900. And chemists tried to make sense of it beyond just having a list of masses and formulas. So the chemist that's most famous that made sense of it is, of course, a Russian chemist named Mendeleev. Okay, so historically he was very interesting, Mendeleev. And this is the kind of thing he observed. Here is what Mendeleev basically found. It's a little complicated to look at this, but essentially here is on this graph is density. And as we go to bigger and bigger masses, this is why we call it the periodic table. Because this, if you think about it as a function, the function is going up and down, up and down, and in regular kind of periods, you see the differences are equal. So this is called the periodic table. The spaces between the two low points would be equal from here to here and here to here. So here, if we look at the density of the element, here's potassium, calcium is less dense, titanium, vanadium, chromium. As we go across the periodic table, the density is going up, and then it starts to go down. And the density is in grams per centimeter. Okay, so this is one thing Mendeleev noted. And actually, he writes in his biography, he was actually trying to figure out a way to teach chemistry. He was a professor of chemistry, and he started writing down the properties of elements on what we would now say are like 3x5 cards. And he would write down the property of each of the elements and then try to arrange the cards in different patterns to see if he could make some connection. Now, let's look at carefully if you can see this. How many oxygens are combining as we go hydrogen, lithium, beryllium, boron, carbon, nitrogen, uh, and oxygen, and fluorine. Let's take this series. It's very illustrative. And hydrogen sort of stands by itself. Let's start with lithium. Uh, Lithium, it took two of them, two lithiums for every oxygen to make a compound. Now, the next heaviest element was beryllium. You look at beryllium has one beryllium per oxygen. And the next element is boron. And here there are the formula is boron 2O3. So it's 1.5 ratio. And here we have carbon dioxide. There are two oxygens. So what's going on is there's more and more oxygens per element as we go up this table. And then it turns around. After carbon, there's oxygen and nitrogen, and then finally fluorine. So the chemical combining power also followed this pattern. Okay, so Mendeleev looked at this kind of thing, and here's Mendeleev memorialized here in a Russian stamp, I guess. And here's what Mendeleev said. I began to look at the elements and write down their atomic weights and typical properties, and the analogous elements and atomic weights on separate cards, and this soon convinced me that the properties of the elements are in periodic dependence upon their atomic weights. That's what we're looking at. And here is Mendeleev's early form of the periodic table. This doesn't look at all like it doesn't remind us of the periodic table we use today, because the elements are going up and down, whereas we have it going across. But let's look at these elements, how we would say. Here, for instance, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay? And then we have another set, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, potassium. So look what Mendeleev did. He arranged these in a sense, what's going on here? The mass is increasing, right? 9, 11, 12, 14, 16, 19. The mass is increasing. Boron, carbon, nitrogen, oxygen, fluorine. Remember? We had the chart. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay? So he was looking at this, and then he arranged them in atomic weight, but he did it periodically. When he got to sodium, he said, I'm going to start a new column. And it started getting longer, and then he'd start a new column. This is what we call today the main group elements, the short columns. And then these long ones are what we would call transition metals. Okay. So he arranged these, and what was remarkable is Why did he put them in columns like this? Because the properties were similar. He found that boron was very similar in chemically to aluminum, carbon to silicon. By the way, how many hydrogens combined with carbon? Is 4. So silicon combined with 4 hydrogens. They formed similar chemical compounds. Nitrogen and phosphorus were similar. Oxygen and sulfur were similar. And so this is why he kept putting them in new columns, so that they would match up across like this. Now, not all the elements had been discovered. So look at what Mendeleev did. This is why he became famous and his periodic table was accepted. He made this list, and then he got to the point where after zinc there was a big jump. You see how the masses only go by 1 or 2 each time? 31, 32, 35, 39, 40. Look what happened. Zinc to arsenic was a jump of 10. That's one thing. The mass jump. This is what the elements that were known to Mendeleev. But not only that, when he did this matching up thing, he found that zinc and magnesium were similar. Arsenic and phosphorus, like arsenic, did not match up. Arsenic, you might have thought, oh, that's the next element. But the properties did not match up with aluminum. Arsenic was much more like nitrogen and phosphorus. So what did he do? He just left these 2 spots open, and he guessed, oh, I think that there should be an element here with an atomic mass of about like 68 and 70. So he did something very remarkable. He predicted elements. And he called these elements with different prefixes. But the ones that he predicted next we called Eka. Eka aluminum, which was the one he said was like aluminum, right? So he lined this up. He said it's going to be like aluminum. So here's aluminum. He said the one that should match up next to it, I'm going to call Eka aluminum. Okay? Then, well, I'm going the wrong way. So what did he say? He started predicting the properties. Now, how did he predict the properties? Well, I have to be confusing and go back again. How did he predict the properties? Well, for instance, he predicted the density. How did he predict the density? Where is okay. He would predict the density based upon what we would call interpolation. Like here's the density of titanium, and here's the density of chromium. And if this was an unknown element, he would say, well, it's like about halfway in between. And he would say that's the density. If there was no dot here, that's how he predicted the density. It was by a process of interpolation. So here's aluminum. He predicted the thing that should be a missing thing that should be by aluminum. Where would that be? Aluminum is here between zinc and arsenic. So let's go back on our column. Here's zinc, and here's arsenic. You can see it's a pretty big jump in mass. So he predicted 2 elements between zinc and arsenic. And he predicted the density just basically as a straight line interpolation. Where would the density be? Okay, so he predicted this Eka aluminum. Okay, and you see here's what he predicted in 1871, and then he published a paper. He said, well, if somebody goes out and looks for an element like this, they should find it. And 15 years later, an element that matched Mendeleev's prediction was found, gallium. So look at how accurate he was. He got the mass close. The density, he said 6. The density was found to be 5.91. He said the melting point would be low. And this is for a kind of metallic element, very low melting point. And he predicted what would the formulas be. Eka-aluminum would be 2 versus 3 oxygens. Here's the formula for gallium. And I cannot put subscripts here. It should be Ga subscript 2, O subscript 3. And he predicted the element of the chloride. Okay, so that was very remarkable, the ability to predict elements. And that's why Mendeleev's periodic table was accepted. Okay, so here's the modern periodic table. And you see what happened is, just for appearance's sake, we kind of turn his on its side. Beryllium, boron, carbon, nitrogen, oxygen, fluorine, Mendeleev put as a column. Well, now we have this as a row, but it's the same ordering. And then we have the next one is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine. So the periodic table is a very powerful way to organize the information in chemistry. If an element is in the same row, it'll have very similar properties. So oxygen and sulfur and selenium and tellurium, what's similar? They all have a formula with 2 hydrogens. Nitrogen, phosphorus, arsenic, what's similar? They all have a formula with 3 hydrogens, NH3, PH3, ASH3. Carbon, silicon, germanium, all like to combine with 4. And so the pattern is actually go across. If you think about how many hydrogens these elements would like to combine with, the pattern is very simple. 1, 2, 3, 4, 3, 2, 1. And then we have noble gases, 0, which Mendeleev didn't have. Same pattern. Sodium, magnesium, 1 hydrogen, 2, 3, 4, 3, 2, 1. And so everything follows. So once you know the property, chemical property of one element, you know something about all the elements below it in a column. Okay. Okay, so that's basically a story of periodic table. Let's okay, so let's go back out of the sharing screen. And okay, so that's our story of the periodic table. Okay, that was a pretty long exposition. How did I do on that? Was that clear enough? Okay, thank you. Thanks for your feedback. Okay. So the yeah, actually, I am recording this. I know you want me to record it. I don't like to record it because I feel like nervous about recording it, but I recorded it. So if you were lost, you can go back and hopefully this can be posted soon and you could take a look. Okay. So yeah, you're welcome to do that. Yeah, I didn't record the early part when we were just chatting, but I started recording when I think when I started doing the slides. So that's more of a presentation. So let's see how that looks. Okay, so what I'd like to do is let's do the breakout group. And this is sort of open-ended, okay? So what I want you to do in the breakout group, pick one of the columns, and what I'd like you to do is the column that is starts with lithium, beryllium, boron, nitrogen, carbon, oxygen, fluorine. So okay, so you got the idea? Your breakout group uh, both physical and chemical properties, both. Okay, so let's say your group takes carbon. You're going to have like carbon, silicon, oh, I can't remember everything. Say you start with oxygen. Your group will take oxygen, sulfur, selenium, tellurium, like that. Each person will take one element, look up the properties, then you will talk about it and compare. Okay? And you can enter the element that you chose and write the properties. And okay? You can pick whichever this is basically your quiz. I'm going to put a quiz there now. It's not there yet. I'm going to put a quiz, and you can each say what your element is, and then enter it. Okay? So just get started, and don't worry about the quiz. It may come a little later, but right now you can start the discussion. Okay? Okay. Uh, we are going to get started now. Let me see. Breakout groups. Here we go. Okay. Bandit's not with us today. I don't know where he is. Okay. Um, mm,
Hey, madam. Sorry.
What are you doing here? Yeah, that's um, yeah.
내가 계속해 이거는 대풀자리 손